There are so many dark clouds in modern physics. Let's go back to classic physics of early 1900s and ask classic questions for elemental particles. Maybe it is time to revisit quantum mechanics and theory of general relativity. This is our new direction of physics.
Today we're going to continue our new direction of physics videos. This is video 7. Okay. It's about the self-interacting field theory. In the last video, we talked about the self-interacting term. So this term is like that, okay? So we see that this term can cause in the bending of the field, okay? Because the original angle is critical, okay? If the mass is so far away, the field is still strong, be bent, because the angle change caused by this term, okay? So at this moment, we are already into video 7, okay? What we're trying to present over here is for the people who have some basic physics background, okay? It's not a PhD or professor level, okay? So we need to get into the details of how the self-interacting field theory works. Then we need the full new general relativity equation or new field equations similar to or modified general relativity. Okay, for example, this term, okay, currently it's 1/2. In the general relativity full theory, this became okay. It's about 1.5 times, okay? No, sorry, it's about 0.75 over 0.5. That's about a little bit larger, okay, than this, okay? So, yeah, about 1.5 times bigger, okay? So the focus in, if we need to study the real effects of this term, we need to go to the modified general relativity, okay? But at this kind of terms, we can still see the effects, okay? Like the binary star, we don't need the full theory, okay? The Kuiper belt, maybe the distance slightly different. If we have the full theory, we may see the angle slightly different, but I'm already using the general relativity version, but not modified. So the Meson star in the between the Jupiter and that, okay? So the Kuiper belt may propose a hydrogen formation, okay? Because the strong interaction and the gravitation are the same field, okay? It's just when it's so strong, they are locally so strongly interact, that's become strong interaction. In the previous video, we talked about astronomy, okay, gravitation. In order for us to go to the micro world, let's see what's the trapping of the field, because we talk about the field being trapped in the 3-dimensional, or it's 4-dimensional. The reason it's space, 3-dimensional, okay? We're not considering time over here, okay? 2-dimensional space on 1-dimensional space, okay? So we will see the field, how it's being trapped, okay? So what I did, we rewrite the Newton's law of self-interacting field theory. We see that the original mass, it's generated the source, okay? And we see that the field, okay, also adding into the mass group, generate the field, but we have this phi. When it's getting to the boundary, this effective mass is very big, okay? So what do we see? I did a calculation, okay? The potential and the effective density, okay? That's this line, it's the effective density. What we did is we put the different scale until 99% of the boundary, okay? So if we see that the potential, the effective density, okay, small, okay, then became infinity, super big. That means within this 99% or 90-some percent, we can still use Newton's law of gravity, okay? This is Newton's law of gravity, okay? So we can still use Newton's gravity. That's why we are able to do this in astrophysics, because we're not near the boundary, okay? So you see that the effective mass is basically very similar until when it's getting to the boundary. But what we see, the potential, it's also once the phi, that's the phi, okay? In the very weak field limit, the very weak field limit, this is equals 1. As the phi goes to 99%, or goes into almost 0, okay? So then we see the effective density. So that means 3D trapping, okay? That means it's only on the boundary. That means that we can still use Newton's law of gravity when the system is spherical, symmetric, okay? Only when it's getting to the boundary. So that means we can still play with Newton's law of gravity, everything's fine, because we're in the three-dimensional trapping. Our boundary is near our boundary of the universe. So that's why Newton's law of gravity, feel free to use it, okay? But when we get to the boundary, but then people say, hey, Q, we don't know the boundary, okay? This is why we see the 3D trapping effect, okay? Yes, we didn't see the boundary, but let's see what 2D bending look like, okay? So in two-dimensional, I mean, if it's three-dimensional plus time, okay? Two-dimension, that means two space dimension. Space dimension, okay. We see that this is the equation, okay? But we see that that's R, not R squared, okay? So if the dark matter density is 0, okay, disk matter near 0, okay, like the galaxy's disk. But disk has enough matter to bend the field up and down of the disk. Let's say we have a galactic center over here, okay? So we have the mass, the field goes out from here and then being bent onto the arm or onto the disk surface. What do we see? The field being bent onto the disk, okay? But if it goes down to the disk, because then the field will be bent back. Because you're away from a mass, then you bend back, okay? But then you're away from this mass, the mass said you come back. It's going to keep going up and down, okay? So that's very easy to understand, the field being trapped in the two dimension. So we will have if we look at it from up, we see a disk like this. The matter will be trapped in this disk. So then the phi is only a function of disk R, okay? Because you don't have three-dimensional. It's a disk. This is 2 pi R, okay? Yeah, in 3 dimension it's 4 pi R squared. That's a sphere. Okay, in 2 dimension it's 2 pi R. So then the force became like this, okay? So we don't have c squared over here, sorry. Yeah. Okay, so, but then the centrifuge force is like that, okay? So then the rotation of velocity around the galactic center, that means the velocity, rotation of velocity, it's a constant. Did we see this? Okay, so yes. Why I'm thinking the 2D trapping, because for example, our nearby star is 4.96 light years away from our sun, okay? So the angle of our sun, the radius over these nearby galaxies, that's the angle, okay? That means you have an angle so far away, the field from the nearby star. Then being focused by our solar system, this angle is bigger. So that means original angle is small, being focused. And then if we have another star, okay, another solar system somewhere over here, so being going to be focused back and forth, keep doing. Especially if we have an asymmetric system like this, the field will be keep going inside the disk. So because the angle, the local angle, is bigger than the angle from the galactic center, okay, or from the nearby star. So the field will be trapped in the 2 dimension. You have a disk. Let's look at it from the beginning, from the top. Okay, we have a galactic center over here. The field will be trapped in 2D. Okay, so that's the angle. Okay, because the angle, it's the bending angle, it's greater than that. That's why the field being keep flowing back and forth. Okay, so that's the picture I showed in the video 1. Okay, so we see that the measured rotation of velocity, that's our sun over here. Okay, our rotation velocity is going around the galactic. So we see that it's almost a constant. That's a constant. Okay. I mean, some people propose that R 1 over R force equals Gm m over R. Okay, but we derived that. We're not proposing. We see the field being bent, being focused. Okay, so because of the focusing, we have 2 pi r. It's the disk. So the field has to go out from a disk. Okay, so we call the density of the field near the rim. Okay, so the density is divided by 2 pi r. Okay, that's the number density over here. If we don't consider because the speed of light, it's constant. Okay, so this is why 2 pi r. So the surface or the line density of the field, it's over r. So that's why we have the r 1 over r force. Okay, so that's a 2D trapping. Okay, I mean, if the angle, the bending angle by the star is bigger than this, it's smaller. Let's go back to the previous video. Okay, if this angle is bigger, okay, the value is bigger, then this is smaller, then you cannot focus. Because if the angle is small, you bend it, it already bent into self-interacting part. Okay, that means they are trapped. Then they keep going back and forth. So if the angle is small, the bending angle is small, like this, okay, then they keep going, dispersed away into 3-dimensional. Okay, if the bending angle is only very small, okay, just like our Jupiter bending the field so small, the field from our sun, okay, being bent small, then they keep going away. But now, if you have a parallel field, where the field angle is so small, it's like almost parallel, okay, so then what you're going to see that it's being focused, being trapped into the 2D. Okay, so the 1D trapping. Okay, so in the 1-dimensional, that's 1-dimensional space dimension. Okay, we don't consider time over here. So then the whole field will be traveling without divergence, because then it's keep going back and forth. Okay, there's no focusing. Okay, so that means the force equal constant, because now if you have 2-dimensional, you're still going away. The r became smaller. The further you go away, it became the 2-dimensional trapping. Okay, 2-dimension is 1 over r. 3-dimension is 1 over r squared. Okay, so 1 dimension the force equal constant. Okay. Okay, so this is very interesting for the micro world. Okay, if the force is constant, and in the microworld the force is so strong, okay, so then the field will have to come back. That's our second question we asked in the first video. We asked whether the field will come back. Okay, field goes out. If force equals constant, force times the distance equals energy. Okay, so that means the force, if it's constant, then energy is proportional to the distance. Okay, proportional to the distance. That means the further you go away, the more energy you need. But you have unlimited energy. So this is why the 1D trapping will be able to, the field has to come back if it's 1D trapping. If 2D trapping is 1 over r force. Okay? If 3D trapping, that's you have a boundary. Okay? So this is why the self-interacting field theory, because of the self-interaction, you have the 3D, 2D, and 1D trapping. No other theory I can see that they have that property. You need a large amount of energy to go away. But you can't go away, because if you go away, you have infinite distance, you need the infinite amount of energy. So this is why in the 3D, in the one-dimensional trapping, okay, then you can't go away. So you go out, come back, go out, come back, go out, come back. Is this virtual particles? I think so. I think, yeah. So you see, that's why we now talk about 3D, 2D, and 1D trapping. The 1D trapping, I'm going to go to the microworld. We need this concept to go to the microworld. So you have an electron, okay, emitting virtual particles, and then that's the Feynman diagram. Okay, you have a P as the electron energy, the energy momentum. You have a K, and then you have a virtual particle emitted and come back. Okay, that's why 1D trapping is important in the microworld. Okay, yeah, and also what's other sense it's interesting. You have in the microworld, you have an electron rotating around the. You have electron rotating around the nucleus. Okay, nuclei. Okay, so it's rotating. In our macro world, we see the electron would emitting radio waves, but the micro world they don't. The micro world field being trapped, they cannot emitting the field away because 1D trapping were causing that you need infinite amount of energy to go away, unless you have a certain property. So this is why the micro world will be quantized. Okay, so is this quantum interaction? I think so. Okay, so we're going to, in the next video, we're going to start talk about the quantum interaction and the micro world property of the self-interacting field theory. Okay, so this is a brief introduction, but for what I'm trying to do over here to see if we can bring the quantum interaction also into the self-interacting field theory. Okay, so in the next few videos we're going to talk about the microworld, because the self-interaction theory allow us to don't have the gravitation constant, but more of interaction, self-interacting. Okay, so it's a closed boundary, and then they have different properties. Okay, thank you.